Okay, so let's continue our topics. So remember that in the previous class for type 0 system, I introduced KP that was G0, if I remember correctly, and we got ESS was, please look at two notes because I'm teaching from my mind, so it's K over P for step input, that's right. And for type 1 system, I introduced KV, that was SG0, and the ESS was 1 over KV for ramp input. And for type 2 system, means it has two integrator, one integrator and no integrator. So I introduce Ka, static acceleration error constant as S square G0, and the ESS was, if I'm right, was 1 over Ka for parabolic input, right? In the table, yeah. It's being recorded. No problem. Okay, for parabolic input, but thanks for letting me know, for double checking. Okay, for parabolic input. And I introduced that G, or transfer function, was sum of T, I don't know, Js plus 1 multiplication of J from 1 to M divided by Sn. N is the type of the system. So, and multiplication from I to 1 to N. And here you have Ti S plus 1. And you have nth order system, this N. But these are the number of what? Integrators of the system. And I provided a table, and I confused at the end because when I was writing from the notes, and I fixed at the end of the class. So these are type of the systems. So after this, now let's go back to our, if you have a y over x closed loop transfer function of the system, and again, whatever I do have here as t prime of js plus 1 in j from 1 to m. And now suppose that the system is nth order, I is equal to 1 t prime of I s plus 1. Means that we have n poles here, n poles and m zeros of the system. So in many occasions, when you are designing your system, you don't know the exact value of the t prime i's of the system. So you have to know for which range of the ti's your system is stable, and for which range of the ti's system is unstable. Stable and unstable. You as a designer of the controller, because when you design controller, this is going to help you a lot. Okay, so that's why I'm teaching you Roth stability criteria. Roth stability criteria. Roth-Horowitz. Okay, Horowitz. If I expand the x over y closed loop transfer function these are the zeros of the system if you have, or numerator. And here, suppose we have this after expanding. A n Sn plus a n minus 1 Sn minus 1 plus a n minus 2 a, oh shoot, and Sn minus 2 plus a n minus 3 Sn minus 3 plus, at the end, a n s naught plus, sorry, n minus n minus 3, 4, 5. A1, I'm sorry, A1 is s to the power of 1. Okay, and finally a naught, and you have n poles of the system. N poles, because this is the power of n. You have n poles. You know how to do it in MATLAB by using the solve command, but everything is not knowing the number of the poles. That's important. Sometimes you have to design the range of stability for these coefficients, for these. And I'm going to teach you as a designer of the controller. So the first condition, if you are done, I will move to the next page. Can I? Yes? Everybody? Okay, so the first condition that your system is stable, first condition. All coefficients exist means non-zero. All of them must exist. Non-zero and be positive. This is first condition. If your system is going to have a stable system, means that a and a minus 1, a minus 2, a, and they all must exist. You cannot have a1 0. You cannot have a not 0. You cannot have a minus 2 0. And all of them must be positive. So an and an minus 1 and a1 and a naught cannot be 0. All of them must exist. And all an and an minus 1 and a1 and a naught must be greater than 0. Must be positive numbers. Being said, if you see such a transfer, closed transfer function of a system, look at here. You don't know even what it is, just by looking at it. I'm telling you, a third order system is like this. 4s squared plus 2. Is system stable or is unstable? What do you think? S cubed plus 4s squared plus unstable, because you are missing what? You are missing what? You are missing s here. So this is plus 0s plus 2. So this is one of the coefficients doesn't exist. See what I'm saying? Okay. So even that if you go to the MATLAB, until it comes up, we can continue. I'm going to show it to you. Second condition is that if the first condition satisfied, okay, You have to make a table. What's the table? Table is this. You have to put Sn minus 1, Sn minus 2, Sn minus 3 to S power of means the constant number. Then in front of that you have to make this table. Okay. So what you're gonna do? You're gonna select these coefficients. Look at here, guys. An minus 2, An minus 4, 6, like that. Look at here. In front of this, the first line, you're gonna put An minus 2, An minus 4, An minus 6, as long as you have. Okay. I want to see. No, it's not. Now you have to select another set of the coefficients. How? I'm going to show you with this color. An minus 1, An minus 3, An minus 5, forever. So you're going to have An minus 1, An minus 3. See? The even numbers 0, 2, 4, 6. Odd numbers 1, 3, An minus 5, An minus 7, and forever that you have. Before going there, let me solve this poles of this system in MATLAB. Okay. Can I? Yes, I can. Why? Because I'm professor. So, see this, guys? If I say sims x and solve this equation, what was on? Okay. Solve s cube. What was the poles? 4s squared. 4. Oh, this is x. 4x squared plus 2. And obviously you have to say double ends. See, guys, has a pair of complex conjugate poles in the right hand side, positive. Do you see that? So it means that your system is unstable. Everybody catch me? This. A pair of complex poles in the right hand side, positive. So you see that even you don't need to do that. See what I'm saying? We don't need it for now. By looking at it, you're gonna say, oh, the first condition unstable. Bye-bye. Just by looking at the coefficients. But you cannot judge it until you try. I mean that it gives you more tools to judge the behavior of the system. Okay? See what I'm saying? So now what you're gonna do, you're gonna, until this point, you are copying. What happened? Oh no, please. For God's sake. Okay. Let's wait a little bit. So until this point, you are copying exactly from the closed loop transfer function. After here, you have to do some operations. What's that operation? That's it. You have to multiply this by this, subtract from this by this, divided by the first. So what you have to do here is n minus 1, n minus 2, minus an minus 3, divided by an minus 1. Next one, exactly the same. You have to multiply this by this again, this by this, divided by a minus 1. So the next gonna be under this. You have to write under this. Okay, see here. So it's gonna be a minus 1, a minus 4, minus an minus 5, divided by again n minus 1. Now the next one. 3 of them is enough. Let me change a color. Here we go. You have to multiply this by this, minus this by this, divided by this. You're gonna have an minus 1, an minus 6, minus an minus 7, divided by an minus 1, and continues until you have. I'm going to show you by examples. See what I'm saying? Now going to the next line, you're jumping to these lines. This multiplied by this, minus this multiplied by this, divided by this. Okay? So I'm naming this as A. I'm naming this whole as B. So you're going to have here this line. A in a n minus 3 minus b a n minus 1 divided by a. Now, the next one. A multiplied by this, and I'm going to say c. C multiplied by a minus 1. So you're going to have a in n minus 7 minus c in a minus 1 divided by a, and continues. Now the next line. So you're going to come to 2 other new until the last line. Last line, you do nothing. You only copy this, the constant number, here, a naught. You're gonna tell me, Payman, are you stupid? No, I'm not. No, I'm deleting everything. Then I'm gonna, when you made the table, you're gonna separate the first column of the table that you made. First column. Here we go. If you are done, I will continue. Can I continue? Yes, guys? Huh? So, the second condition that your system is stable, the first column of table must exist, means non-zero, and be positive. Here we go. All of them must exist, and all of them must be positive number. This is called the Roth stability criteria to judge the stability of a given system. Now, we have some points. The number of sign change in the first column shows the number of right hand side poles. Interesting, right? Let us start with our previous trivial example. This y over x was 1 over s cubed plus 4s squared plus 2. By just looking at it, you see that it terminates the first condition. It's missing s. So your system is unstable. MATLAB showed to you. But let's go to our table. S cubed, s squared, s1, s0. So the closed loop transfer function is this. S cubed plus 4s squared plus 0s plus 2. What you're gonna do, as I said before, you're gonna select this and this and this and this. In S cube, you're gonna 1, 0. S squared, you're gonna have 4, 2. Last line, I told you that you're gonna select the constant number 2. Here, this multiplied by this minus this multiplied by this divided by 4. So you're gonna have 0 minus 2 divided by 4. Yes or no? Huh? How much is this? Minus 0.5. Yes, everybody agree? Yes? So let me delete everything because now we know the answer. And just put minus 0.5. Now I select the first column. Okay, all the first column exists, but one of them is positive or negative? Negative. This is negative. So your system is unstable. I told you the number of sign change in the first column shows the number of right hand side poles. This is one sign change, another sign change. How many right hand poles we have? 2. And remember the MATLAB that I just ran to you? It had 2. It was like this, if you remember. Plus, I don't know, just a number, 3i. We had the pair of complex conjugate poles. That's right. Here we go. Bingo. Everybody understand? Yes? Good. Now, let me go to another example before going to the parameter. So y over x, closed loop transfer function, is 1 over s4 plus 5s cubed plus 10s squared plus plus 4s plus 20. I don't know. Just give me a number. A fourth order system I'm teaching in ME430 this semester for 2 spring mass and damper and spring series. Fourth order system. So by looking at these coefficients, all exist and positives. The first condition, bingo. Second, you have to make the table S4, S cube, S squared, S1, S0. It is this 1, 10, 20. Now you have to do this 5, 4, nothing. Here is 0. It is 5, 4, and here is 0 because there's nothing. Okay. The last line is how much? You tell me. What's here? The last line? Tell me. What's the last line here? Yes, 20. Here we go. Now, 550 minus 4 is how much? 46. 46 divided by 5. 100 minus 0 divided by 5 is how much? 25. Now this line. This multiplied by this minus this multiplied by this. So let me okay. 5 multiplied by 10, 50 minus 4. That's right. This multiplied by this minus this multiplied by this divided by 5. Now this multiplied by this 100 minus 0 divided by 5 is 25. No, yeah. Okay. So this is 20. What? Here? Okay. Okay. This is first line. Right? 1, 10, 20. Yes or no? Now the second line. 5, 4. Do you see any number here? See what I'm saying? Now, for the next line, you have to multiply this by this. You have to multiply this by this, divided by this. So let us do that together. 4 multiplied by 46 divided by 5 means 36.8 minus 100. Oh, come on. It's gonna come. Okay. Divide by 100 and divided by this number. 46 divided by 5. 9.2. The answer of this is, for God's sake, 36.8 minus 100 divided by 9.2 is minus 6.8. So I'm going to delete everything and put it here only. Minus 6.86. Now I'm going to delete everything to make it clear. Okay, good. Now I have to select the first column. I have to select the first column. Here we go. 1, 5, 46 divided by 1 minus 20. Is your system still unstable? Unstable. Why is unstable? Well, one of them is negative. How many right-hand poles we have? Yes. Sign change from this to this. What's wrong with this, guys? From this to this and from this to this. So you have two right-hand poles. Understand, everyone? So, and it's obvious if you go to MATLAB, you can find these two right-hand poles. Okay, everybody? Can I go to next problem? Yes? Okay. So, what? Y over X is this. I have to play the numbers in my mind, okay? Bear with me. Okay. So this is the system. Here we go. So the first condition, all exist on positive. Bingo. Second, we're gonna move like this. 1, 5, 4. 1, 5, 4. The next round, 2, 10, nothing, 0. 2, 10, and 0. Now let's go to the next line. Last line is how much? Here? You tell me. What's the last line? 4. There we go. Now, this line. 2 multiplied by 5, 10. Minus 10 is 0. Okay. 2 multiplied by 4. Okay. Minus 0 divided by 2. Gonna be 4. That's it. Now here. 0 minus 8 divided by 0. So how much it's gonna be? 0 minus 8 divided by 0. How much is this? Minus infinity. Okay. Can anybody judge the stability of the system? No, because here you have a 0. Okay. When you have a 0, you have to have some auxiliary points here. See what I'm saying? So what you're gonna do, you have to say, when you have a 0, I'm gonna replace it with epsilon plus a very small number. Okay, so now you're gonna have 10 epsilon plus minus 8 divided by epsilon plus. Okay? Understand what I have done? When you have 0, you have to replace it. Obviously, by looking at it now, you can judge it, because this is positive, this is positive, this is positive, this is positive, but this is negative, but is it some number? That's right. Now you can say that the system is unstable. See what I'm saying? You have to have some number there. So if I go to the MATLAB, let me go to the MATLAB. Okay. And if I solve this problem, seems x again, and solve, can you give me the equation? x4 plus
S4
provided plus 10x plus 4. x4 plus 2x cubed, 5x cubed, 10, right? So, and I'm gonna say P, and I'm gonna say double P. You see, we have 2 right-hand poles. See here? 2 right-hand poles, as we know. 1, 2. Oh, sorry. 1 from positive. Because, you know why? Because I changed the epsilon plus. If I remain it as 0, 0 has no sign. See what I'm saying? You cannot judge the number of the right-hand poles. See what I'm saying? So, but here I see this is a positive number to negative, negative to positive. Now you have 2 right-hand poles and the prob, and it says a pair of complex conjugate poles in the right-hand side. 1, 2. So you got the point of why I changed the 0 with epsilon? Yes? Everybody? Good. Let me go to the next problem.
A quick question.
Yes. And divided by 2. See what I'm saying? Never forget this, guys. Look at here. Good question. All of them, they have divided by this, divided by a, and going down, okay? See what I'm saying? If you see epsilon plus, which was 0, 10 minus 10 divided by 2 is 0. I don't care. Okay? See what I'm saying? Now let me go to the next problem. I have to play with the numbers a little bit. You have to give me time. Okay. Okay. S5, fifth order system, plus 2S4 plus 5S cubed plus S square plus S plus. So it's going to be S5, S4, S cubed, S square, S1, S0. Okay. 1, 5, 10. One, 5, 10. Here we go. So if you look at this, fifth order system can be a RLC circuit or whatever it is, the reason. This with this, this with this, this with, here we go. 1, 5, 10. 1, 5, 10. Now the next line. S4, 5, 5, 10. That's it. 1, 5, 10. 1, 5, 10. Now, last line is how much? Now you know it. What's the last line? Yes. Now let's go here. 5 minus 5, 0. Divided by 1, 0. 10 minus 10, 0. Divided by 1, 0. Oh, you stuck here. Because everything that what you're going to do, it's going to be 0. So here, you have to do this. You have to get auxiliary polynomial. Polynomial. When you have a 0 rows, not one only this element, 0 rows, everything is here 0, you have to have an auxiliary polynomial. How? Look at here, guys. You have to say P of S, you have to make like this polynomial. This one was S4 plus this 5 was for S square. 5S square. Just from this line, above that, this line of this rows of the 0. And this 10 was from here. Do you see what I'm saying? This is 5. 1 S4 plus 5 S square plus 10. Then you have to have derivative with respect to the S. dp over ds gonna be 4s cubed plus 10s. Then simply you have to replace the coefficients instead of the zeros. See, s cubed, s cubed. So here it's gonna be 4, here it's gonna be 10. Simple like that. Everyone understand? Yes?
Yeah.
Good. So now you can do it. 4 by 5, 20. Minus 10, 10. 10 divided by 4, 2.5. Right? What? Yeah, sure. So did you follow this? Okay. This line we select the line above all the zeros, okay? This line. Okay? Let me redo it again. No problem, man. 0, zeros. We select the line above the rows of the zeros, this line. Okay? This line coming from here, that's right, from the polynomial, from the denominator. 1 is S4, that's right, the coefficient of this. Remember that we got from here, that's right? So S4 plus this 5 is for S square, right? 5S square plus This 10 is from here, plus 10. Okay. Then we get derivative with respect to the s. Gonna be 4s cubed plus 10s. Now, now you see the s cubed, s cubed. I'm gonna replace the coefficients here, 4 and 10. 4 and 10. Understand? Now we continue because now we have numbers. 4 by 5, 20, minus 10 is 10, divided by 4 is 2.5. Understand? And here is 0 actually, because there's nothing. 40 minus 0 divided by 4 is 10. Here we go. Right? This multiplied by this minus this multiplied by this divided by 4. Everybody understand? Yes? Now this by this. The next line. 25 minus 40. 25 minus 40 divided by 2.5, which is a negative number, guys. Now we select the first column. Here we go. System is stable or unstable? And how many right-hand poles we have? Positive to negative, negative to positive. 2. Bingo. But this auxiliary polynomial is this one exception of both time. When you have the zeros, one row of the zeros, you have to use this. Now if I go to the MATLAB, just read the equation for me, okay? S5, what was that? Read for me the rest. Plus S4. Okay. If I say double P, see you have 2 right-hand poles. You have totally 5 because fourth order system. You have 2 right-hand poles, a pair of complex conjugate in the right-hand side. Yeah, here, as I told you, we have 2 sign change. 1, 2. I'm not sure that you wrote this, but I taught you. The number of sign change in the first column shows the number of right-hand side poles. Do you see that? Good. So, but it continues because I told you, because these days MATLAB, you don't need to do this for understand this, but we're going to use the row stability to determine the range of stability for the system parameters. See what I'm saying? For the range of the parameters when we design and control. Okay, guys, so let me stop it here and don't leave. Okay.